Welcome to The Explainer. Today, we're going to talk about a leap that every developer has to make, going from just writing code that, works, to engineering software that is genuinely reliable, robust, and built to last. We're going to dig into how a disciplined approach to testing can give you the freedom, the confidence to build and change your code without constantly looking over your shoulder. Oh, you know the feeling. We've all been there. You make one tiny little change you think is completely harmless, you run the app, and boom, the whole thing comes crashing down. It's that sinking feeling in your gut that just kills your confidence and makes you afraid to even touch your own code base. But what if it didn't have to be like that? What if you can make any change, big or small, knowing you had an automated safety net ready to catch any mistakes? What if you could refactor and improve your code without any fear at all? Well, that is the promise of a really solid testing strategy, and it all starts with one powerful idea. So, how do we start building this safety net? It all begins with the most fundamental building block in modern software, the unit test. Okay, so here's the key idea. A unit test zooms in on the smallest possible piece of your code. We're talking a single function or a method. We call this a unit, and its entire job is just to prove one thing, that this one tiny piece does exactly what you think it does, completely on its own, isolated from everything else. Now, the best unit tests aren't just thrown together randomly. They follow a super clean, really clear pattern that everyone understands. It's called the Arrange, Act, Assert pattern, or AAA for short. And trust me, it makes your tests so much easier to read and maintain. Let's break it down. It's a simple three-step dance. First, you arrange. This is your setup. You create all the variables, all the objects, anything you need to set the stage for your test. Then, you act. This is the main event. You call that one single function you're actually testing. And finally, you assert. You check the result. Did the action produce the outcome you expected? Yes or no. Simple as that. And here's what it looks like in action. It's super straightforward, right? First, we arrange our world by creating a new calculator and our two numbers. Then we act by calling the one method we care about, add. And finally, we assert that the result we got back is, in fact, 15. This clean three-part story is the beating heart of every single great unit test. Of course, in the real world, things are a bit messier. Our functions don't live in a perfect little bubble. They need to talk to databases, call external APIs, or interact with other complicated parts of the system. So to truly test our little unit in isolation, we need a way to manage all those connections. And this is where senior engineers pull out a few clever tricks. To solve this dependency problem, we use something called test doubles. Let's look at the two most common ones, stubs and mocks. On the left, you've got a stub. Think of a stub as a simple stand-in. If your code needs to fetch a user from a database, the stub just hands back the same fake user every single time. It's predictable. Then on the right, you have the mock. A mock is more like a spy. It can also provide fake data, but its real superpower is that you can check how it was used. You can actually ask the mock, hey, did the code I'm testing call your save method exactly once? These tools are what let us test our logic without ever actually hitting a real network or a real database. Okay, so we know how to write a good test, but now let's talk about when we write them. And this leads us to a really powerful and kind of counterintuitive discipline called test-driven development, or TDD. This isn't just a way to test, it's a whole new way to think about building software. You heard that right. With TDD, the test comes first. Before you've written a single line of the actual feature, you write a test that describes what you want that feature to do. And of course, since the code doesn't exist yet, the test fails. But that failure isn't a bug, it's the starting line. This is the very first step in the famous Red-Green-Refactor cycle. You write one small test for one tiny piece of behavior, you run it, and it fails. It turns red, and that's a good thing. It proves your test actually works and that the feature isn't already there by some accident. Now, your one and only goal is to make that test pass, to turn it green. And here's the rule. You write the absolute simplest, bare minimum code you can think of to satisfy that test. We're not trying to be clever or elegant here. We're just trying to get to green. And once the test is passing, once it's green, now you have a guarantee that your logic works. This is the refactor step. This is where you can go back and clean up your code, make it more readable, improve the design, and get rid of any mess, all with total confidence. Because if you accidentally break something, that test will immediately turn red and tell you. and then you just repeat this little cycle over and over again. Now, I know what you might be thinking. This red-green-refactor dance sounds slow, but the long-term payoff is absolutely massive. It is the direct answer to that fear we talked about at the beginning, the fear of breaking things. So what do you actually get for this discipline? So what's the big payoff? Well, first, you get high test coverage basically for free, because you literally can't write any code without writing a test for it first. Second, it leads to better design. Seriously, when you write a test first, you're forced to think about how your code will be used, and that naturally pushes you towards smaller, more focused, and loosely coupled pieces. Third, and this is the big one, you get that safety net for refactoring, the freedom to improve code. And finally, your test suite becomes living documentation. A new person on your team doesn't need to read stale documents. They can just read the tests to see exactly how the system is supposed to behave. This right here, this gets to the absolute heart of it. Testing isn't really about finding bugs after the fact. It's about enabling change. It's what turns a fragile, anxiety-inducing codebase into a resilient, adaptable system that you and your team can evolve with total confidence. So I'll just leave you with this thought. Maybe we should stop thinking about software as something that we just write from top to bottom. What if instead the best, most robust, and highest quality code isn't written at all, but is carefully grown, one tiny, verifiable, and well-tested step at a time?